Thanks very much. Questions?
Hi. So for the reconstruction noise, it is only the Gaussian part, right? The reconstruction noise for the KZ, is only the Gaussian part? So there will be also a non-Gaussian part which will add, because the NL reconstruction noise is only the Gaussian noise.
That's right, yeah. So with the large scales, if you try to reconstruct this very good. I mean, the velocity is just linear to your velocity.
So you are saying the non-Gaussian part is not contributing much to the KZ power?
That's right. I mean, if you see where the velocity dispersion comes from, for example, galaxies, it's completely dominated by the linear dispersion. And then, of course, there will be a little bit of KZ inverse spectrum, and that we have not quantified.
And what about the RSD effect?
RSD, yeah, so RSD do matter, and it's kind of the same way as photosis, either erase structure along the line of sight. So for the K values which we are talking about, we checked and even RSD are not. We're really talking about reconstructing from 100 megaparsec down to horizon scale, and they would definitely make a difference on smaller scales, but these are very large scales, and much larger than the velocity dispersion. The distance, you're equivalent to the velocity dispersion.
So, hello, here. Hello. Thanks for the very nice talk. KSZ is a very faint signal, and so there is also the primary CMB. So of course here scales matter, I mean angular resolution, but there is thermal SZ effect, and there are relativistic and non-thermal SZ effect, plus foregrounds. Is that a worry?
Okay, so yeah, so foregrounds add a noise. So to lowest order foregrounds add a noise and not a signal, not a bias, and simply because of this symmetry of plus or minus V. In other words, in our estimate, you're weighting half of the galaxies with positive sign and half of them with negative sign because of the probability of having a negative velocity. And that means that things like dust emission or TSV, they have a constant sign. They are always the same sign for all galaxies, so they largely cancel out. Okay? Then you have residual effects, and like Emmanuel maybe will show a plot of which we estimated how much residual TSV just due to the discrete number of galaxies you have. But on the top of that, of course, that's noise. Okay, and that noise is included in this forecast.
And how does it compare with the instrumental noise?
So normally, I mean, the power of foregrounds at a few thousand is about 5, 6 microKRK depending on your model. So when the instrumental noise is larger than that, then you're mostly instrumental noise dominated, and not. They quickly become the dominant source when you go below 5 or so microKRK temperature. And of course, multi-frequency analysis helps, but it helps kind of fairly slowly to reduce the power. But that's included, like it's based on an ISC.
Any more? Okay, let's thank Simone again. So next we have Emmanuel Sham.
I'd like to start by thanking the organizers for putting together this nice conference and for this opportunity to speak. So my name is Emmanuel Sham. I'm a postdoc at the Lawrence Berkeley National Lab. And I would like to mention a few examples.
thanks very much. Any question on those 3 or 4 talks?
I have a question to you. We know that all the foregrounds, apart from kinetic SZ, have a different spectrum than the CMB. Are you saying that your way of isolating the shear is better than having 5, 6, 7 frequencies?
No, so of course there are many different methods to get rid of the foregrounds through map. And the point is that this method is uses a slightly different set of information. So usually, like you say, some foregrounds have different frequency dependencies. If you have observation at many frequencies, you can remove some of them. That's not the case, for example, for KSE. That's the only one that is not the case. And it has been shown alone yesterday, right? But this, in a sense, is something you can use on top of that. So this doesn't rely on the frequency dependence of the foregrounds, it relies on their spatial state. So in a way, this is independent information for this, something you should
You didn't say much about the details of the source of these fluctuations, the feedback or whatever. Presumably you could use very deep radio source counts and distinguish perhaps star formation, winds, AGN, very weak AGN at some level. But they might all be playing some role in these fluctuations, right? Yeah, I mean these would induce velocities that would, give you some possibly KSE signal too on these very small scales, right?
There are obviously many other probes in that information. One reason the KSE is interesting, so I know that's an absolute question, but what's unique about the KSE is that it's near convex. And this is something you won't get from, say, thermal temperature, nor in X-ray where you get square, so in that respect, KSE is somewhat unique.
That's right. I mean, you mentioned feedback, but there are various sources of feedback that could induce these tiny velocity fields that you'll be measuring by KSE. Right.
So the method that I presented, which relies on this velocity reconstruction here, basically recovers the velocity on the darker scales. And so the field that I showed that was blue and red is computed from hundreds of gigaparsecs. So basically what the velocity coefficient that I'm detecting here far goes better than the rest of the molecules. So I'm not sensitive to knowing the
So I'm curious about your thought on a recent almost detection by Feng and Holder, who don't use a specific estimator but try to model the bispectrum. So what are your thoughts on this?
challenge, therefore, is do you need to subtract that non-Gaussian estimator? So in that paper, this is basically what they find. They take a quadratic estimator and they apply it to the CMB map. They find significant cross-correlation with various tracers of the matter. When you just do this, the non-Gaussian signal is quite a bit larger than your Lansing signal. And so you might be nervous about whether you'd be able to subtract it completely. In fact, this question is what motivated us to look at those shear estimator. So this is something it's work in progress, but it seems that if you apply that shear estimator to your CMB Lansing map, this non-Gaussian bias is reduced by a lot. So it's left to see whether it reduces enough. But yeah.
Any final question? Okay, let's thank Emmanuel again. So next we have Moritz Munchmeyer.
Hi, so I'm Moritz. I'm a postdoc at Cosmology Institute.
Right, thank you. Questions? No, it was too clear.
Thank you.
Okay, let's thank Moritz again. It might be the top. So the last speaker for today is Giulio Fabian.
Can you hear me? Yeah. Okay, so I'm Giulio. I'm a postdoc at Sussex, and also the last enemy standing meeting you and dinner. So I will try to keep it on time and hope to keep you awake. So I'll basically tell you about some numerical and theoretical results that came out in the last year. So about the modeling of CMB Lansing in light of the future experimental sensitivity, including also cross-correlation with Lasker structure tracers. So I don't have to convince you that CMB Lansing now is a powerful cosmological probe after Planck results. And up to now, we have modeled this effect in the so-called Born approximation, which basically tells us that the trajectory of a photon that we receive in our telescope is actually a photon coming from an original direction theta displaced by this quantity here that is given by a gradient of this phi potential, which is a scalar potential that consists in basically the projection of the whole dark matter distribution along the line of sight between us and the last scattering surface. We can reconstruct the map of this potential from the data, and this is the results by Planck. But this year we reach a milestone in a sense that the latest SPT Lansing results reach the limit where the reconstruction of CMB Lansing done from polarization data is more sensitive than the one done in temperature. This is really important because in the future, observation of CMB polarization will allow us to improve even more the sensitivity of this kind of measurements. Now, once you have these very nice maps of the dark matter, you can also do cross-correlation with the Lasker structure tracer because, like I said before, the CMB Lansing, it's an integrated map of the dark matter. So all the things we see in the largest in the Lasker structure surveys also have a signature in CMB Lansing, basically. So usually we compress this information in the cross-power spectrum that gives us a weighted, let's say, information on the matter power spectrum depending on which probe you use. For example, you can use galaxy counts or weak lensing galaxy surveys. And in the last few years, there were lots of results coming out exploiting this kind of techniques. There was also probably the first cosmological application of cross-correlation with the DS results in 2016, where they basically created this estimator DG that is an estimator of the growth function, independent of the galaxy bias. And this statistic will become very competitive, as you can see here, with future surveys like LSST, SO, and CMB-S4. Now, we also heard many nice things about systematic marginalization in weak lensing survey in Elizabeth's talk, so I don't think that I have to add many more details on that. So in the coming years, CMB measurements will improve a lot. And so we'll improve the sensitivity of the polarization measurements, and this basically will allow us to push the noise on the lensing reconstruction from this level with Planck with this level of SO. So we're going to measure with a high signal-to-noise many modes, and with CMB-S4, we basically have signal-dominated measurements up to L = 1,000 of the CMB lensing potential. And if you look at this plot here, basically on this angular scale, you can see that you're going to essentially start imaging structure on the quasi-linear and nonlinear regime. So there are many things that we want to revise in the approximation that we usually made, in particular concerning the impact of the nonlinear evolution on CMB lensing and also on the Lasky structures when we do cross-correlation, and the validity of the Born approximation. So we know that there are many potential wells in the universe, and the photon is defected multiple times during its journey towards us. Okay, so a bit more context on this post-Born correction. So since nonlinear evolution is sort of easy, but this is a bit more exotic in a way. So if you consider two consecutive lenses, in the Born approximation, basically what you do is saying that your deflection is the sum of the deflection computed, given by these two gravitational potential wells, computed with respect to the unperturbed line of sight. But if you have a first lensing event, your ray converges on the second one. And the ray is closer to the potential well, and the deflection is stronger, and this gives extra lensing. However, if you look at, let's say, a bundle of light rays that are lensed by the first lensing event, basically the images shrink and shear, and this reduces the cross-section that you would have on the second lensing event. So this creates a net decrease in lensing. So there are two competing effects given by these corrections. Now, how we can model this? I spent a lot of time developing a simulation method to do this quite accurately, revising some early effort of people in a way. So basically, I'm using a suite of embodied simulation very large, like 2 gigaparsec, 2048 cube particles, to create maps of the lensing potential, including nonlinear corrections. We basically apply randomization and replica technique to fill in the volume of the universe, let's say, where we do not have a precise snapshots in time. And we slice the light cone into a series of volume that we project in a different lensing plane of surface mass density. And once you have that, you basically have all the ingredients to do ray tracing. So you can propagate your ray through each lensing plane through the so-called multiple lensing approximation that is basically given by this equation here. So the ingredients are this U matrix, which are second derivatives of the matter, the photon trajectory at a given plane, and the back distortion tensor. And this distortion tensor basically encodes all the second-order effects. And you can also propagate the same light ray in the Born approximation, assuming that this matrix is the identity. So you have a very precise way to compare post-Born and Born observables. Now, let's cut to the chase. So what is the effect on CMB observables? So let's start from two-point function. So the multiple deflection will basically change the power spectrum of CMB lensing, and you have here the fractional change, which is very small. It's like 0.1%. And the simulation results match very well the analytical prediction that were developed at the same time by a series of people here. The other nice thing is that we basically measure very well the so-called Carl deflection, which basically are, let's say, a peculiar effect of the post-Born, so of multiple deflection due to the coupling of lensing. And they also match very well the analytical prediction. But both of these are basically undetectable for the future. Now, if you look at the same kind of effect, so nonlinearities and post-Born effect on the Lansing power spectrum, basically we get a 0.2% effect, so very small. So here you have two colored lines that basically show two different ways of computing this correction. The simulation was so precise that basically allowed to see this tiny difference in the way you compute these corrections analytically. So also this one will basically be undetectable, but the good news is that we can model this effect very well if we need to do it for some reason. Now, so why, if we cannot see it on CMB lensing power spectrum, if we cannot see it on CMB power spectrum, why do we care at all? And the answer is here. So the main effect of nonlinear evolution and post-Born effect show up in higher order correlation function. So here I show basically a plot taken by this paper here of the CMB lensing by spectrum induced by the nonlinear evolution. This is a strictly positive quantity. This tells us that overdensity grows faster when you already have an overdensity. Okay, it's an auto-positive correlation, positive feedback. And if you start including post-Born correction, you have that the equilateral configuration of the bispectrum are enhanced, while the more squeezed ones are suppressed. They become negative. So the overall effect of post-Born effect somehow is reducing the non-Gaussianity. Okay, and here you have basically the total contribution. Okay, keep this in mind. Now I'll tell you why this is important. So we have, when we write down the standard estimator of CMB Lansing, we basically combine two CMB fields through a convolution kernel, okay? These are lensed fields, it's the stuff that we observe. Now, you can develop in series and say, okay, my lens field is the unlensed CMB plus some correction. At first order, it depends by one phi field. It's a gradient of phi. And when you plug this expression here and compute the power spectrum of the Lansing potential, you basically have to compute a 4-point correlation function, and somehow you can form some combination of fields that, once contracted, basically survive only if you have non-Gaussian statistics. So this term here only show up if you have a non-Gaussianity in the Lansing field you want to reconstruct. So basically, if you neglect this effect, you bias your Lansing estimation. Well, we developed an accurate way to measure this effect, and you see here basically the bias in terms of fractional difference with respect to the true power spectrum from different Lansing reconstruction channels using temperature, polarization, or the minimum variance combination that uses all the possible combination of CMB fields. You have a very nice effect here, so the nonlinear part creates a negative bias, while the post-Born one a positive one. So difference in sign that cancel out the effect. Okay, and the effect it's much larger for temperature, because temperature is much more sensitive to the small-scale modes where you get, let's say, a stronger impact of the nonlinear Lansing as well. Now, if you push these things to cosmological parameters, it's quite interesting to see that basically, if you just consider one of these terms, one of the two terms, only post-Born or Lansing structure, you have shifts in cosmological parameters that basically follow the same sign of these biases. And different cosmological parameters are more or less affected, but I show here the example that is most interesting, I think, which is the one of the neutrino mass. So we are trying to fit the data set that we simulated and trying to recover the input of the cosmology that we put of our embodied simulation and of our CMB that has 0 neutrino mass. And the more you include the CMB modes at smaller angular scales, so you increase your Helmholtz, basically your bias becomes higher and higher. And this is driven by the temperature that is, again, more sensitive to this nonlinear evolution. And you can basically find yourself in a situation where you can detect a non-zero neutrino mass at a couple of sigma evidence, and this effect is only due to the fact that you neglected these higher order biases. Okay? If you compare, for example, this dotted line here with this colored line here, which is the same experimental setup, but combining CMB with BAO, you will see that this bias goes away. And this tells us that you need to be very careful in the future, because you can find inconsistency between data sets, CMB only or CMB plus BAO, that might only due to these effects that are left unaccounted in the likelihood somehow. Polarization, again, is less affected, so we may also have inconsistency between Lansing estimated from parameters derived using Lansing estimated from polarization and the one from temperature. Okay, now what happens if we reconstruct our CMB Lansing and we correlate it with the Lansing structures? The intuition, I think it's useful to look at this plot, where you have here a slice of the bispectrum in equilateral configuration for galaxy Lansing, or for Lansing of a source plane located at different redshift. Okay? So is redshift 1, black is the redshift of the CMB. And sorry, it's the dotted line here. And you can see that basically it grows because nonlinear evolution becomes more important. While the solid one here is the same thing, but for the post-Born term. And you can see that it has the opposite trend, okay? So when you correlate with the large-scale structure tracer, you basically pick up, you end up only picking up the nonlinear part and reducing the post-Born part. There is no overlap, okay? And this breaks the cancellation effect, and these bias effects might become more important. So you can model this thing analytically, and that's basically what was done in a paper that came out last week. And it's actually a bit more simple because you have less term and less contraction that can survive. And basically the difference between the auto-spectrum case is that now these bias depend on the cross bispectrum, where you have one field that is your large-scale structure tracer, galaxy density, galaxy Lansing, and two CMB CMB Lansing field. Now, we want to test eventually our modeling on simulations. So we developed a set of coherent simulations using the same pipeline. It's very easy to adapt. We simulated, here you have an example of the accuracy we get on weak Lansing power spectrum, weak Lansing convergence power spectrum, and also weak Lansing rotation power spectrum. So these are second-order effects that were never tested at this level of accuracy in any simulation before, to my knowledge. If you correlate then the simulated Lansing field with the CMB Lansing, you get across a very good agreement with theoretical predictions. Here you have basically a scatter plot in a way, where I show the difference of our simulation with respect to theory computing with different model for the nonlinear matter power spectrum that shifts around of about 2%, which is consistent with the inherent theoretical uncertainties that we have. So if we plot now the trend of this entry Hals bias in cross-correlation, we can see a few different interesting things. So the first one, in solid line here, you have the amplitude of the post-Born part of this bias. When we correlate with galaxy density, it stays constant with the redshift because the effect grows in time, grows as the line of sight grows, but also the overall signal we are after grows the same way, so it stays constant. While the nonlinear part here keeps growing when we go at low redshift. And this basically gives the fact that when we correlate with tracer at low redshift, this bias becomes more important because you have less cancellation. On the bottom, a quick comparison of this kind of biases that you would get in the minimum variance combination for SO in solid line and for S4 in dashed. And you can see that with increased sensitivity and we will boost these biases by a factor of 3, and depending on the scale you're looking at. And again, this increase in bias is due to the fact that we assume here that with S4 we can reconstruct Lansing using temperature up to Lmax 4000. So temperature really drives the effect here. Now we can compare these results with numerical simulations. You have on top the entry Hals bias for with cross correlation between CMB Lansing and galaxy Lansing of sources at redshift 1. And you can see two things, for example. The solid and dashed line basically use two different recipes to compute the theoretical prediction. So two different fitting functions for the matter bispectrum. So at S4 sensitivity, we will have theoretical prediction that will differ depending on which kind of fitting function you use. So it's really important to improve our knowledge and capability to model accurately the matter bispectrum. And temperature again is big, but the overall minimum variance effect is greatly reduced. And if you go at higher redshift, here you have the cross correlation with galaxy density at redshift 1. So weak Lansing at redshift 1 plus matter at redshift 0.5, so it's slightly more nonlinear. So the higher you go in redshift, the agreement with theoretical prediction that we have become remarkable. So I'm going to skip this one because I'm running late. So let's come to detection prospect. So of course, this depends a lot on how you optimize your future large-scale structure survey. But if we take the minimum variance combination of Lansing and shot noise of 3 galaxies per square arc minutes, which is more or less the shot noise of future survey like Euclid and LSST, we're gonna basically detect this entry-Hals bias with high significance, in particular for galaxy lens with a high redshift beam. However, we can correct for that, and this dashed line here shows basically the detection significance that we would get if we corrected the data with our theoretical prediction. So basically, it's using as a signal the residuals between the theoretical lines and the dotted line and the dots here. Okay. Yeah. Okay. Let me just say 2 things about that. So this this effect is also nasty because it can mimic the effect of intrinsic alignment in the cross correlation between CMB lensing and galaxy lensing. So if you want to marginalize intrinsic alignment effect, you have to include or get rid of these effects. Otherwise, you would detect a fake intrinsic alignment signal at 5 or 3 sigma, depending on which redshift beam you're looking at. Cross correlation with density, same thing. You're going to detect it at high significance with S4. Also with SO, if you start doing a tomographic analysis and you'll have sample variance cancellation. It's basically my last slide. So we heard about alternative estimators from Simone. So thanks for from Emmanuel. Sorry, thanks for the nice introduction. And here I show the entry-Hals biases with different estimators. So this blue line solid is the reference one that I showed in previous slides, and the other colored ones are the one that you will get with alternative estimator that are designed to deproject foregrounds. So depending on the redshift, you can the use of this estimator might reduce a lot these biases, but there is a trade-off between getting rid of the biases and decreasing your overall signal to noise. So I skip to the conclusion. So in the upcoming high sensitivity regimes, the approximation that we usually use needs to be revised. And so we did that in many different ways. And we found out that nonlinear effects and postbone effects are negligible on any 2-point observables. However, at higher order, they show up as this entry-Hals bias. They can prevent cosmological analysis, and they are more important for cross-correlation. We also validated and developed and validated analytical modeling of this effect that allow to mitigate all these effects and recover essentially all the science case. And as a last point, I would like to stress that there is also, so these biases come out only because we're using a quadratic estimator, so we don't know if these biases are there if you use more optimal estimator, and more work needs to be done there, and we leave it for the future. Thanks.
Any questions? I can't ask questions because I'm in the paper as well.
Right.
Okay, let's thank Giulio again.
Right.
So before we go to dinner, I have an announcement about